Okay, so we're in chapter 12.1. We're talking about sequences. So here's the definition of a sequence. A sequence is a function f whose domain is the natural numbers. The terms of the sequence are f of 1, f of 2, dot, 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 f of n, dot, dot. Okay, so what does that mean? The natural numbers are in the domain. That means if we have a function, something like this, the only numbers that we put in are natural numbers, like 1 or 7 or 5. We don't put in 5.3, we don't put in -4. So the only numbers that we put in for n here are going to be natural numbers. That's what it means that the function has a domain that are natural numbers. Now each of one of these guys, f1, f of 2, f of 3, f of 4, f of 5, f of n, we like to use notation that just says, hey, that's the first term a, that's the second term, that's the nth term. So the way we annotate them is if it's a1, that's the first term. And if it's a2, that's the second term. If it's an, that's the nth term. Okay? So here's an example of a function right here, f of n equals 1 over n. So the first term we would say is f of 1, which is 1 over 1, which is 1. Okay? F of 2 is 1/2. Okay? F of 3, the third term, is 1/3. F of 4 is 1/4. And so what we do is we create the sequence of terms 1, 1/2, 1/3, 1/4, 1/5, and so forth. Eventually we'll get 1 over n, and then we'll just keep going. Okay? This is the sequence of numbers. It's a sequence of numbers. All right? Now, so I've defined formulas for the nth term. This is a sub n. So the nth term looks like this. So find the first 5 terms and the 100th term of the following. So what's the first term? a1. So if I put in a1, n is 1, I'll get 1 over 1 plus 1, which is 1/2. There's the first one. a2, 1 over 2 plus 1. That's 1/3. a3, 1 over 3 plus 1, 1/4. Okay? How about this? a4, 1 over 4 plus 1, which is 1/5, and a5, 1 over 5 plus 1, which is 1/6. Now if I want to find the 100th term, I just simply put a100, which is 100 divided by 100 plus 1, which is 100 divided by 101. Okay? Very good. Now, here I have a little bit different. Looks real complicated, but you'll see what this turns out to do in just a second. If I want a1, I get -1 of the first power is -1 divided by 2 of the first, so it'll be -1/2. And if I go a2, then I'll get 2 squared on bottom, so I'll get 4 on bottom. -1 squared is +1. a3, I'll get 2 to the third. -1 to the third makes it negative. a4, 2 to the fourth, 16. -1 to the fourth power is +1. a5, I'll get 32, and -1. What this -1 to the n power does, it makes it what we call alternate sign. Alternate sign. So it goes from negative to positive to negative to positive to negative to positive to negative to positive, and so forth. And the 2 to the n just takes each of those inputs for n in the domain and raises 2 to that power. So 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, 2 to the fifth. So if I want a to the 100, okay, we know it's going to be 2 to the 100 on bottom. I don't know what that number is. It's a big number. Well, is it going to be +1 or -1 on top? Well, 100 is an even number. You notice at all the evens, it's positive. So we'll have 1 over 2 to the 100. Okay? So this is just us introducing what exactly a sequence is. A sequence is kind of just a group of numbers that are defined by some function. Okay? So we have a sequence of numbers. We write about next one, first term, second term, third term, fourth term. It's a sequence of numbers defined by a given formula. In this case, we had this formula. In this case, we have this formula. Here we have this formula. Okay? Sometimes we want to go backwards. Sometimes what we'll be given is we'll be given the actual sequence of numbers, and we want to find a formula for it. Okay? So I've got a problem here. It says find the nth term of a sequence. That is, find a formula that defines a sequence whose first several terms are given. Okay? So I'm giving you the terms. What we got to do is we got to be able to find the formula that would create these terms of the sequence, okay? Well, sometimes it involves just playing around with it, but if you look at this first one, I've got 2, 4, 8, 16, and so forth. Okay, well, these look like all powers of 2, don't they? Well, this is 2 to the first, this is 2 to the second, this is 2 to the third, this is 2 to the fourth. And if you see it that way, 2 to the first, 2 to the second, 2 to the third, 2 to the fourth, really aren't we doing is we're saying the first term is 2 to the 1, the second term is 2 to the second, the third term is 2 to the third, the fourth term is 2 to the fourth. Therefore, the nth term would be 2 to the n, correct? So our formula will be an equals 2 to the n power. Okay, that gives us a formula for this sequence of numbers. All right, let's take a look at number 2. Now, kind of similar to what we talked about before, we have this idea of alternating. So we'll deal with that separately than what we deal with the bottom. Now we'll look at the bottom, we have 3, then we got 9, then we got 27, and 81. Again, those are powers of 3. It's very similar to this. So this kind of looks like 1 over 3 to the 1, and then I have 1, and I'm not worried about the negatives right now, 1 over 3 to the second, and 1 over 3 to the third, and 1 over 3 to the fourth. So the nth term, right, that nth term down the road will probably be 1 over 3 to the n. Now, the issue is, what do I do with this negative? Because it is alternating negative, positive, negative, positive. And if it's alternating negative, positive, and the first one is negative, we can always just stick a negative 1 to the 1. And then here we'll have negative 1 to the 2, because these two have to match up. Negative 1 to the 3. And you see how that if we do that, again, even exponent makes it positive, odd exponent makes it negative. We get exactly what we want. So this will be negative 1 to the n power. So my formula will be an equals negative 1 to the n over 3 to the n. Okay. Next one. All right, well, I'm going to rewrite this. This is going to be 1 over 1. Okay, I'm just going to rewrite it a little bit nicer. All right, now the denominators, these are not like these ones where I took a base and I raised it to an exponent and that exponent changed. Here, 1, 4, 9, 16, 25, don't those look like the perfect squares? So the next denominator will probably be 36. Well, that's 1 squared, and that's 2 squared, and that's 3 squared, and that's 4 squared, and that's 5 squared. So if I got to the nth one, it'll probably be n squared, won't it? Yes? And then what's happening up top? 1, 3, 5, 7, 9, I've got odd numbers, correct? Well, a couple ways that we need to be able, a couple things we need to know is if I want to describe an even number, all even numbers have the form 2n. For example, if n is 1, it'll be 2. N is 2, it'll be 4. N is 3, it'll be 6, and so forth. And all odd numbers have the form 2n minus 1. So if I put in n equals 1, I get 2 minus 1 is 1. N equals 2, 4 minus 1 is 3. So we know that the numerator then will be 2n minus 1. So my fourth term, 1, 2, 3, 4, if I put in 4 here, I should get this. 4 squared, 16. 4 times 2 is 8, minus 1 is 7. So this is the form excuse me, for the nth term of that sequence. Now we're going to talk about recursively defined sequences. So what does recursively mean? Recursively means you define the first couple terms and we define the next terms off those previous terms. And our second example will make quite a lot of sense because you may have been exposed to this before. There's some famous movie trivia involved in this one. But let's take a look at this first one here. So suppose I define my first term to be A1. So right, if I'm writing a sequence out, my first term is A1. Okay? Well, then what's A2? Again, that's A1. A1 is right there. I want to find out what A2 is. Well, by this formula, I'm defining A2, n is 2. Actually, why don't I write it this way? So A1 is 1. A2, according to this formula, A2 equals 3 times A, n is 2. 2 minus 1 plus 2, right? Well, isn't that equal to 3 times a1 plus 2? Because 2 minus 1, of course, is 1, right? And we know what a1 is. a1 is 1, right? So 3 times 1 plus 2. So this is going to equal to 3 times 3, which is 9. Awesome. Let's take a look at A3. Well, A3 is 3. A3 is 3 times 3 minus 1. A3 minus 1. 3 minus 1 is A2 plus 2. Okay, which is 3 times, what was A2? Well, that was 9. So I get 33. A4, notice this is always 1 less than this one. So if this is A4, that's going to be A3. So I'm defining new numbers off of doing adding and subtracting and multiplying off of old numbers. So this will equal 3 times A3 is 33 plus 2, which is 35. It's 105. Okay? And you keep going on this like forever to get the sequence of terms 1, 9, 33, 105, and so forth. So that's the sequence. Okay? This next one you'll find to be pretty interesting. So if I write A1 is 1 and A2 is 1, well, A3 is A3 minus 1. 3 minus 1 is A2 plus A, again, we're talking about N is 3. 3 minus 2 is 1. So A2 plus A1, A2 is 1, right? A1 is 1. Good. What's A4 then? A4 is equal to A4 minus 1, which is A3, plus A4 minus 2, which is A2. Well, A3 was 2 and A2 was 1, so I'll have 2 plus 1, which is 3. All right? A5. A5, well, let's see if we see the pattern. A4 is A3 plus 2. A3 is A plus 2 plus 1. A5 is going to be A4 plus A3. You're starting to see the pattern, right? Because that's 1 less, and that's 2 less than that guy. So that's going to be 3 plus 2, which is 5. A6 is going to be A5 plus A4, which is going to be 5 plus 3, which is 8. So our sequence of numbers is going to be 1, 1, 2, 3, 5, 8, 13, 21, 34. And you'll notice that each number is the sum of the previous two. This one is the sum of the previous two. This one is the sum of the previous two. This one's the sum of the previous two, and so forth. That's the way this is defined. Each number is the sum of the previous two. And this is actually called the Fibonacci Sequence. After that guy, and is actually famous in that movie, what's the name of that movie with Tom Hanks? I forget the movie. You've probably seen it before. All right. There you go.